And that's because Intel and the PC community started focusing on the efficiency side of the equation. And so we think there's a similar opportunity in electric vehicles to stop this trend of ever bigger, heavier, and more expensive batteries by making the utilization of the energy more efficient.
On this episode of Embedded Insiders, Jack Weast, Intel Fellow and Vice President and General Manager of Intel Automotive, breaks down the company's recently announced OLEA U310 SoC. Built with a hybrid and heterogeneous architecture, the solution is designed to improve the overall efficiency of electric vehicles by promoting energy efficiency and lower design and manufacturing costs. Next, Rich and Vin are back with another Dev Talk discussing the embedded developer's approach to the testing process, specifically the pros and cons of waiting to test prototypes once they're complete, and the testing tools every developer should have in their toolbox. But first, Rich, Ken, and I discuss the current state of electric vehicles and our curiosity about Intel's approach to the market. Hello, everyone, and welcome to the Embedded Insiders podcast. I'm Associate Editor Tiara Oliver, and I'm joined, as always, with Executive Vice President Rich Nass and Senior Technology Editor Ken Briota. How are you guys?
Great. How you doing, Tiara?
Doing good. So, I wanted to share a recently received press release that I got from Intel with you guys. I decided to take it a step further and reach out for an interview, and I was able to speak with Jack Weast, their Senior Principal Engineer and Chief Systems Architect for Autonomous Driving Solutions at Intel. So he gave me a breakdown of the company's recently announced OLEA U310 SoC, which, according to the press release, is designed to streamline e-motor technology, specifically driving down electric vehicle design and manufacturing expenses, and overall promoting energy efficiency. So I kind of just wanted to see what you guys thought about this, until getting deeper into the electric vehicle market.
I'll go first. I think it's actually pretty cool because we've heard so much talk about the compute aspect. NXP has been spending a lot of time talking about being the brains of the car, but now we're actually talking about the powertrain, and this is pretty different. And I don't think that there's been nearly as much focus on the powertrain as there needs to be. I in Intel's words, they're talking about revolutionary, and I hate the use of that word, but it is something that's really important, and nobody's really taken the bull by the horns. Is that the right phrase there? Taking the car by the transmission to whatever it is, but I do think it's an important part of the EV that has not received its due.
Yeah, and obviously the EV has a definite advantage because you can find efficiency through software in much greater ways than you can with internal combustion or more traditional vehicles. Revolutionary is probably a stretch. I will be happy to allow companies to say they're revolutionary when their electric vehicle rises up against the government and creates a new system. That's a revolutionary vehicle, if you ask me. But I will say I'm a little bit skeptical about how much impact in terms of cost of the vehicle that fuel efficiency is going to have. Obvious, or not fuel, but you know what I mean, energy efficiency is going to have, because obviously, that might decrease the operational cost of the vehicle to the end user and the consumer, but the initial purchase cost is tied so tightly to battery, to that I think that we're not going to see electric vehicles get cheaper than gas-powered vehicles until the battery technology improves and gets cheaper and we figure out a new solution there. I think so much of it is tied to that it's hard for me to believe that something as simple as operational efficiency is going to affect the bottom line too much. I don't know, maybe I'm wrong. It's happened before.
I don't know as much about it as Tara does from interviewing this guy, but if we can charge less, I think that's where you're seeing the savings. It isn't in the car itself; it's in the operation of the car. Because if you can get a longer runtime, depending on how much longer, but if you can get a longer runtime and not have to charge as much, I think that's where you realize your savings.
Tiara, feel free to jump in here as we speculate, but with the expert info.
I mean, I was going to just leave it up to the upcoming interview and let our listeners hear what he has to say.
Yeah,
that makes sense. So let's
rather than hear
let's
our
do that.
speculation, we want to hear the actual truth, huh?
Yeah, I guess. Fine. How about some expert opinions?
My name is Jack Weast. I'm an Intel fellow as well as the vice president and general manager of Intel Automotive. I started at Intel in 1997 to date myself as an intern with computer science background. So joined Intel full time in 1999 as a software engineer and had a variety of technical roles all across the company. Worked in consumer electronics, worked in our research division, worked on networking products, a couple different stints on automotive related things. And so am now to be honored to be leading our global automotive business for Intel.
Awesome, and congratulations.
Thank you.
So we'll be talking about, the somewhat recently announced Intel's new SoC for electric vehicles. And of course, there's a lot of talk and fluctuation in the market as far as electric vehicles. But before we get into Intel's solution, can you tell us what Intel's role has been previously in this market? And maybe what made you guys want to launch this product and maybe what the goal was with it?
Yeah, it's a great question. So historically, people know Intel for our high performance compute products. So we're in, I think, upwards of 40 million vehicles on the road today have Intel products inside. Predominantly, that's infotainment products. So these are chips that are driving the displays in your car, whether it's the navigation screen or it's the instrument cluster. We also have networking products, FPGAs, a variety of different things out there. But that's predominantly what people think of when they think of Intel. But when we looked at the challenges that the industry was facing, certainly they need help embracing a software-defined architecture for their high-performance compute systems. And so that's where our infotainment product line continues to grow up to embrace a software-defined architecture and things like virtualization and containers, et cetera. But elsewhere in the automotive ecosystem, and particularly the transition to EVs, we saw an opportunity to help the industry with one of its second biggest challenges, which is the cost of electric vehicle platforms. Batteries are getting bigger and bigger, more expensive, and it's difficult for automakers to make a profit on their electric vehicles. And electric vehicles of today kind of reminded us of mobile computing 20 years ago. When I first started at Intel, your laptop weighed 5-6 pounds or more, and you got about 45 minutes of battery life. Today, you've got thin and light systems that last all day. And that's because Intel and the PC community started focusing on the efficiency side of the equation. And so we think there's a similar opportunity in electric vehicles to stop this trend of ever bigger, heavier, and more expensive batteries by making the utilization of the energy more efficient. And so as we look deeper into energy delivery systems inside electric vehicles, we saw a lot of inefficiencies. Typical modulation algorithms that are used in electric vehicles today are very inefficient and have a lot of loss and leakage in the form of heat, which means you're losing energy, but then you've got to manage that heat. And so we felt it was time for the industry to embrace a new approach for managing energy within the vehicle. And so just like AI requires new kinds of products, we've developed a new kind of product for the power space. And so that's the product, the OLEA U310 that we announced recently.
And then I know you mentioned, the market needs of energy efficiency and cost, and I guess overall ease of use. Can we dive into a little bit of the architecture of this SoC and kind of how, those market needs that you just mentioned, how your product is designed to meet those?
Sure. So if you think about energy flow within a vehicle from, say, the wall, if you will, to the e-motor, you've got 100% kind of theoretical energy that comes in. Then it goes into an onboard charger device. Then it goes into the battery management system where the energy is put into the cells. Then it goes through a DC to DC converter, and then it goes through an inverter and finally reaches the motor. By the time you reach the motor, you've got 60 some percent of the original 100% of energy, theoretical energy. And at each one of those stages, you have loss. And loss shows up in the form of leakage and heat, which then needs to be cooled and managed with also expensive thermal cooling solutions. And so the goal is try to reduce the amount of loss at each stage of that energy flow. And so we have a device that is a unique kind of new power control SoC. And so it has elements of a microcontroller, elements of an SoC, and elements even of a programmable kind of accelerator device, all in a single product. And what it does is it allows automakers to use entirely new kinds of modulation schemes that are not possible to run on current systems. Traditional modulation approaches have been used for decades in the industry, and they work. But they're showing their age in terms of their inefficiency as we go to ever higher voltage batteries and motors. But there's an entirely different class of modulation algorithms out there, like optimized pulse pattern, for example, which works based on the rotation angle of the motor rather than a timing-based switching model, which is how traditional pulse width modulation works. And what that does is it allows you to be much more precise in terms of when you're delivering energy, and means then you have a lot less loss and a lot less leakage. And so you get then a higher performing system that needs less energy. But these algorithms, don't work on traditional solutions. Traditional solutions in the market are a microcontroller or a DSP. And just like, a large language AI model is not going to run on a simple CPU. Same is true for these new class of modulation algorithms like optimized pulse pattern. The performance that they require is just not possible on a traditional microcontroller or DSP. So that's why we need a new kind of device which has acceleration capabilities so that you can adapt the chip and really get silicon level performance for these algorithms. So tens of thousands of times faster switching capability is achieved now because we have a device that was designed for these kinds of next generation modulation algorithms.
So before we get to the algorithms, because I think that's obviously super important and I want to get to that, you did mention that the solution is kind of a combination of SoC and microcontroller and maybe some other things. How does that, maybe help your goal of trying to simplify this technology if you're kind of combining things? Does it, is it more so adding on rather than taking away, or is there another way you guys are able to simplify this kind of combination?
Yeah, you're spot on actually, because this chip is like many different kinds of chips in one. It definitely allows the automaker to combine and consolidate what might have been 2 or 3 discrete chips on a power module control board into a single chip because of the kind of many in one capabilities that it has. So that's absolutely part of the design of the chip. And this is also more important when you think about ECU consolidation. So not even just within one ECU can you combine 3 chips into one, let's say, but now we can support, let's say, both onboard charging and DC to DC conversion and e-motor inversion in a single device. So really have multiple ECUs come into one ECU and one chip. So now you're talking about combining 4, 5, 6, 7 discrete products into one because our product supports that consolidation of these kinds of workloads with silicon force separation to ensure there are no safety or performance implications. So it's absolutely a consolidation play, which helps automakers save even more cost while we make energy delivery more efficient, which enables them to save more cost as well in terms of lower voltage batteries, or they can shrink the size of the motor, cheaper thermal solutions, smaller capacitors. So the system level implications of this new design are quite significant when you start adding up the cost savings that can be achieved across the vehicle by simply swapping out your existing power delivery solution with a modern next generation approach to delivering energy.
And then getting a little bit more into, the software stack, can you maybe explain or give us a brief breakdown of the software stack included with the OLEA solution? And then maybe a little bit of the role that the advanced algorithms or AI has in performance enhancement?
Sure. So with this product line, we provide multiple different pieces of software and tools for customers to use. We do have our own implementations of some of these algorithms I mentioned for different applications like onboard charger or in-motor inversion or DC to DC conversion that are already optimized for the silicon. So if an automaker or tier 1 or tier 2 partner would like to take a solution that is known to work and known to be optimized and already proven to deliver all the benefits that I've been talking about, we can offer that complete solution. Other customers might have their own teams that like to pursue their own algorithmic approaches. And so for that, we provide both libraries as well as tools that allow designers to work directly in a model-based design approach where we can take their models from MATLAB, for example, through our tools directly into the silicon. Or a customer could just take a wide open approach and use traditional C, C++ type application development for our product. So our philosophy is really to provide choice and flexibility to our customers. That's a hallmark of how Intel approaches computing generally from a commitment to open platforms. And so we do that here as well, while also providing already optimized solutions if customers want the fastest time to market with something that is already known and proven to work. And then for the, oh shoot, I'm sorry, Tiara, I forgot the second part of your question. My apologies. What was it?
No worries. I know I was kind of stacking them on there a little bit, but I just kind of wanted to know a little bit more about the role the advanced algorithms or AI has in enhancing the performance of the OLEA for, electric motor control.
Yeah, okay. Yeah, so in terms of the role that our product uniquely plays with these new algorithmic approaches, one of the interesting things to think about is algorithms like optimized pulse pattern have to be precisely tuned to a specific motor or battery combination. And so that's why in typical modulation approaches, you do this in software. The problem with software is microcontrollers and DSPs are severely performance limited to run these next generation algorithms, which require thousands of orders of magnitude more performance that simply cannot be delivered by a microcontroller or DSP. And so what you'd want is an ASIC, a custom piece of silicon. But the problem is you can't build an ASIC for every different combination of motor and battery, for example, that's out there. And so the solution is in our device, we have a portion of our device that has programmable acceleration logic. And so you can go from your optimized model-based design tools where you've done in simulation the fine tuning that you need for exactly the behavior of the motor at different performance points. And so you can do that in the lab, and then you can put that model directly into the silicon. So it doesn't run on an application processor. It actually gets embedded into the silicon and performs at a level like it was an ASIC. But now you're getting the programmability benefits of using model-based design and software, but you're getting the performance benefits as if you had built a custom piece of silicon to do it. So that's what uniquely allows us to run these next generation class of algorithms in a device that still meets automotive power requirements and more of a classical, kind of microcontroller envelope. So it's a very unique kind of device. It's we think a one of its kind, but we think is a better approach for the industry going forward to embrace future algorithmic approaches, just like many other industries have evolved beyond, classical approaches and are embracing new, AI approaches instead.
So you touched a little bit about integration and compatibility. How does the OLEA solution integrate with maybe existing electric vehicle architectures and components? And then, what are some of the challenges when you're integrating this OLEA solution with various electric vehicle platforms from different manufacturers, for example?
Yeah, from an integration standpoint, it integrates in many cases seamlessly. So if you're an EV maker and you've got a power module that's doing inversion for your e-motor, let's say you've got a IGBT or silicon carbide MOSFET board, and then you've got a control board on top, and then all that's wrapped up into a box, which is put into the car. And so in many of our first customer engagements, where automakers get a chance to compare side by side the performance and efficiency and see the huge benefits that we offer, it's as simple as swapping out their current box with a new one that fits exactly the same footprint, compatible from a connector standpoint and everything. So honestly, in many respects, it's transparent from a vehicle design. They just immediately get to see the performance benefits. And then they can start looking at the system implications of, wow, now that my vehicle is operating much more efficiently, I can buy, DC link capacitors that are half as big and cheaper. I don't need as an expensive of a thermal solution anymore because there's less heat dissipation that I have to worry about. And these downstream effects start rippling. You can shrink the size of the motor by 25% and get the same performance. So these downstream effects are really amazing once you simply swap out a box that you've got. So we have reference designs with companies like Wolfspeed, for example. So if you've got an existing box, you can easily swap it out and get a boost, get an upgrade over your current approach. Now, if the automaker would like to kind of dig into more details and do some of their own algorithmic development, here too, if they're doing all their work in model-based design tools like MATLAB, which was what most of them use today, we can go directly from what they already have that works on what they're using today, and then put that model into our silicon and see the performance improvements and benefits. So we try to make it as seamless as possible. For customers that don't want to get into all the details, but for those that do, we also provide a platform that is as open as possible as well, so customers can explore their own innovative algorithmic approaches and take entirely new vehicle design approaches because of the benefits that this offers at the same time.
And then since, we're in the era, I guess, of cyber resiliency, I do have
Mm-hmm.
to ask, what security features are embedded in the solution, to protect against cyber cyber threats and to ensure the safe operation of EVs?
That's a fantastic question, actually, and I think something that is a big challenge for the industry because you think about the lifetime of a vehicle's deployment and the rate of advancement in new threat vectors, or whether we're going to enter a post-quantum crypto era sometime in our lifetimes. Who knows? Maybe sooner than we might expect. Suddenly, that's going to be of paramount. I mean, of course, it's a top concern today, but it could be of extreme concern in the future. And so we're taking an interesting approach to that, which we think provides automakers with even better protection than what they're doing today. And that is, first, we meet all of the industry standard hardware security module requirements that the industry requires. So we meet or exceed all of those requirements that exist today. But second, what's novel is how we implement that. In most cases, your hardware security module is a fixed device that meets the spec, implements the standard, and that's it. If a new threat vector happens in the market, or let's say a different geography, a different government, requires some different sort of implementation, you typically can't adapt those hardware security modules that are out there in all these vehicles to work for new approaches. In our device, we leverage the programmability aspect of our chip to put the hardware security module in part of that programmable logic. And so what that means is if even after post deployment, some new, some attack on a widely used, crypto scheme is unleashed, we would be able to even reprogram in the field upgraded protection against those new threats. Automakers can also use the same device across multiple geographies where there might be different crypto requirements in certain regions. They can have the same part, but just program it differently depending upon where those cars are being sold, versus having to have 2 or 3 different discrete parts in their supply chain. So bringing that programmability aspect to the security functions of the device, we think makes a lot of sense in a world where nobody knows, what the latest algorithm that's going to get cracked is going to be. And so we've got to be resilient for the future and support even in-field updates and protection against new attack vectors that could come in the future.
Sounds great. And then kind of looking forward, what can we expect to see from Intel, in the future regarding electric vehicle development and maybe even SoCs with this exact architecture or similar?
Yeah, so what's interesting is we're finding that this new product, this OLEA U310 that we announced, our original intention or first application, let's say, was for these power use cases that we've been talking a lot about today. But at the end of the day, if you look at the design of the chip, there's really nothing inherent about it that's specific to power. At the end of the day, we have a high performance, kind of microcontroller class SoC with unique acceleration and programmability capabilities that are a perfect fit for anywhere you have deterministic real-time control algorithms. And those kind of algorithms are prevalent all over the car. In body or chassis functions, for example, braking. And so what's next is exploring with automakers is could we also take this design and apply it to more generic zonal kinds of use cases where you have further opportunities to consolidate 3, 4, 5 ECUs into one and do that even more efficiently than current approaches, which typically involve just adding more cores to a microcontroller to consolidate workloads. With our approach, we can deliver higher performance, lower power, greater efficiency, even for non-power workloads compared to existing approaches. So that's something that we're already actively exploring with a number of automaker partners, and we're excited to see what the industry will do with this technology next.
Now, here's Rich and Vin back with another Dev Talk discussing the embedded developer's approach to the testing process.
Welcome to the Dev Talk podcast with Rich Nass and Vin D'Agostino. It's been a little while, Vin. How have you been?
Yeah, I've been great. How have you been?
I'm okay. I won't go into detail on the dental surgery that I had, which is why I probably sound a little funny. And if we were on video, you'd know that I look a little funny, but I will survive.
I'm sure that you will, and I'm sorry you're going through that. It's been, I think it's been a crazy summer for everybody. Everybody's had something going on that I've been talking to. So it's just one of those years.
Well, unfortunately, I'm at that point in life where a lot of your conversations are about doctors and insurance and stuff like that.
Oh, don't start that. Don't start that. They don't have to be.
Okay. All right. So the topic du jour is test. And this is one of those subjects that I keep coming back to that I don't know if people don't take it seriously enough, or they think it's one of those it'll never happen to me kind of things. But embedded developers seem to think that they should test their prototype when it's complete. And you and I both know that that's a mistake. But why can't we convince the community that that's the wrong way to approach test?
Well, I think look, there's a few things. We talk about embedded systems, and that's what we do. Um, but this is also in mechanical engineering and chemical engineering. As engineers, we want to see something happen, right? I talk to people about being almost 65 years old and still getting excited the first time the LED flashes, right? And so we want to get to that LED flash point. But I think that when you're working on a product, it's really important that you know that you can verify upfront that your intent is met. It has far-reaching implications in not just in the design of things, but in the manufacturing of it, and even in field service. Right there are we all know stories about cars, typically sports cars, that are designed that you can't get a spark plug unless you drop the engine because nobody ever thought about servicing it or testing it in the field. And so there's a lot of things that if you do it up front, testability in quotes is something that, just like batteries, just like security, all the things we've talked about, if they're done from inception instead of tacked on afterwards, they are always more effective. And
okay, let me stop you there.
Yep.
Because I think we need to define something. When you say testing from the beginning, I think the developer says, well, what am I going to test at this point? I don't have anything to test. So what is
Right.
it that you're referring to?
So you're referring to, I've just designed this. How do I know that it works? Right? Mathematicians do this all the time. They have a way to test their hypotheses as they're building the hypothesis. There's a rule in manufacturing that you can't test quality in. You have to put it in from the beginning, and the testing is just there to verify that the process was followed properly. So I think that thinking about how you're going to test something when you design it has implications not in just the way you write code, but the reusability of that code. Because if you design it in a way that it's testable as a module, then that module can be reused, right? So the money that you spend up front on the test, you get back on the back end and get back again when you reuse code, for example, or a circuit that's already been designed and proven, because you haven't just proven it for that one case, but you've proven your initial assumptions for why you designed that code or that circuitry or that board. I'm working, I love war stories. I'm working with a client right now who's trying to figure out how to test some boards that they're having made after designing them. And we're now just figuring out where we can clip test leads. Luckily, there's a capacitor that's laying down, so there's a place to clip onto ground, because as the board was designed, as the circuit was designed, there was never any thought to how am I going to verify this afterwards? Do I have test points, right? We are now looking at having to do better nails or some other way to get it pins on connectors because we don't have test points in place to be able to easily put a probe without shorting against something else. So, that's when I say that if you don't do it up front, the end cost is more. Sometimes in a tight design, if you had a couple of test points, you could use regular test leads. You don't need to build a test fixture. In a tight design, without thinking about that, you're now building a test fixture. That's cost, that's maintenance, that's timeline, right? So those are the things that if you think about them up front when you're designing a circuit or when you're designing a piece of software, you can definitely have some advantages down the road. Design for testability is a thing in software development. When you are studying computer science, one of the things that you talk about in class, if you're in a good school, is design for testability. How are you going to know that the algorithm that you've just designed works in all the corner cases, so the plane doesn't get in the air and a corner case comes up and the flaps move the wrong way or something, right? These are all critical things. Not everything is life-threatening. Sometimes the light just doesn't turn purple when it's supposed to. Oh well. But if you design this stuff, if you've designed the testing into this stuff from the beginning, it means that all along your process, you can verify that what you thought you did is actually what you did do. It sounds like a pain in the butt. It really does, but it makes having that light flash when it finally does more enjoyable. It really is.
Okay, so let's talk about some of the tools somebody should be using to do this testing process. I assume you're talking about debuggers and things like that. And what about more hardware related stuff?
We're definitely talking about debuggers. We're also talking about philosophies when you don't have a debugger. You know, those people who do Arduino designs, they don't have a debugging interface that plugs in, although the new generation of Arduino has come a long way for that. And figuring out where in your code you might want to print a value of something to see that you can trace the value and it's doing what you're expecting. That's all part of figuring out how do I know where this input's coming from, what its limits are. It's about starting. I mean, before you're ever doing anything with hardware, whether it's a hardware design or even the hardware interfacing to software, you need to sit down and figure out what your input is going to be in the range of it, what the output is going to be and what you expect, and some kind of transformation model from inputs to outputs. Sometimes that's simple, right? It's an amplifier and it has a gain of 3. Okay, that's easy. But if you have an integrator that has a maximum output value because it's going to another stage that has a maximum input voltage before you blow it up, you know, there are things that you need to take into account as you're designing, and that's more complex. So on the hardware side, there are even times when you need to open up a loop to be able to test it and then close it for operation, right? So a lot of people say, well, just unsolder that resistor. Now all of a sudden you're modifying a board that was made in manufacturing under a controlled condition. You don't want to do that, right? I'm just talking to another customer who needs to make 2 versions of a board, and they were going to swap 2 resistors out. And I said, if you do that, you're now hand soldering components. You'd be better off putting them in and having one with a solder bridge. So you're just dropping a solder blob in, and now everything but that last solder blob is done in a controlled manufacturing environment. And that is actually going to work out really well for them. So it's thinking ahead. And it's like driving, right? You don't drive in the next 5 feet. You drive, looking out, a few car lengths. So you know what's coming up.
Where'd you come up with that analogy?
I just did right now. I'm sorry. I just did right now.
Okay.
And so, on the software side, it becomes a little dicier because there are sometimes things you can't see. You actually have to probe in to see. It's not physical like a circuit on a board. And figuring out where the interfaces are, where the challenges are, and where things might go wrong and monitor them. And of course, again, if it's not a safety critical thing, or if it's not a motor that's going to slam into a wall with a robot arm or something, you have the luxury of running it and seeing what happens and then saying, okay, that was not a response that I expected. So where could that have gone wrong? And you may put breakpoints in to look at values. You may log values. You may end up keeping that log live for a while so that when something weird happens, you can go back and look at it, right? There's what I would call instantaneous testing, where you can make something happen and you can look at what's going on in those conditions and figure out how to control them or monitor them or somehow compensate for them. And then those weird things that just happen every so often. And if you aren't logging data and able to look at the correlation of it, then and you may end up monitoring things that aren't that important. You and I a few weeks ago, maybe a couple of months ago, had a conversation about data collection in AI, right? And when you're designing AI, you might look at 100 different parameters and then analyze it and realize of those 100, only 3 matter, right? But if you weren't monitoring those 100, you don't know that you would have captured the right ones. And so there are times even in testing where you're going to look at something that maybe doesn't make sense, and all of a sudden correlated with something else, it does make sense. So it's about correlation.
Okay, so let's really do the listeners a service. Let's name some names. Give me some tools that should be in the arsenal of a developer.
So I think anyone working with a circuit needs the minimum of, more than one multimeter and an oscilloscope. That's the starting point, right? You might think that it's DC, and and your digital multimeter may tell you it's DC, and then you look at it and there's a ton of noise on it and it's filtering out. So you need to be able to look at signals for sure. I would always suggest that if you could afford it, you get a 4-channel scope so you can look at things again for that correlation of what's happening with multiple signals at the same time. On the software side, everybody should have a debugger. Everyone should start by getting, one of the first things I do is get a serial port up when I'm working on a micro, because if I don't have enough memory to log something and keep it in RAM on the device, then I need to put it somewhere. And so being able to pump it out a serial port when I'm working on that, and you can say, well, my debugger, blah, blah, blah. But I've worked on systems where you put it in system and it's, running at 120 volts, and your only option to do something safely is to have an optically isolated serial port where you're spitting out conditions and values, and you're watching it as the entire system is going through its process. And you can say, oh, that sensor didn't happen when I thought it was going to happen. And I need to compensate for that, or I need to look at it differently, or I need to move the sensor, or I need to do something, right? So sometimes it's a physical response in the system, sometimes it's electrical, and sometimes it's a piece of software. You need to create a low pass filter for something because there's some noise on a sensor that you hadn't planned on, right? And you won't know that without being able to monitor. So everybody should have a debugger. Everybody should have some kind of optically isolated magnetically isolated serial connection to their system, even if they're not using it in the final throes of things. Everybody should have test points on a board. And I'm a big believer in LEDs. You don't have to load them in manufacturing if you don't want to, but if you've got the room, you put them on the board, you put them on your prototypes, and you can see some conditions immediately by doing that. And then you just make them do not stuff for your production if you don't want to spend the money. I've had a lot of field people thank me. I've been in a lot of low volume companies, right? Not people making cell phones and stuff like that. So if you're making 5,000 of something, having a few extra LEDs doesn't break the bank, right? And I've had field service people say, thanks for putting that stuff on. I was able to solve the problem right away because I could see that light didn't come on and I knew the sensor was broken. I didn't have to do anything. So it's not just about designing for your own testability or even testability in manufacturing. It's even what's going on in the field.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.